Hey guys, so today what I want to do is talk about variance, standard deviation, and standard error. Sometimes these terms can cause confusion. They're of course related to one another. And while I'm talking about it, I want to talk about the parametric population and our sample population once more, because all of these terms are used in the context of both the parametric population and the sample population. So let's start with the variance. And typically variance in the parametric population is going to be given by sigma squared. Okay, and when we look at sigma squared, it's simply the sum of squared deviations from the parametric mean over all observations, right? And we divide by n, the number of individuals in the parametric population. Typically, our sample population will be an estimate of that, and we use the letter s squared to indicate that, and to talk about the difference between it. So the difference is going to be, we're going to subtract the estimate of the parametric mean from the observations, and summed over all I observations, and divide by the n of the sample. And this is going to be an estimate of the parametric variance. So again, think of our theoretical world over here that we're trying to make inferences about. And then this is our sampled world, our statistical world, the real world, if you will, which we have time, resources, money, etc. to actually to make inferences about this world from. Okay, so we have our parametric variance and our sample variance, and there's typically when we have a small sample size, in fact, for virtually all real-world samples, we're going to have to put in the denominator here degrees of freedom, which is n minus 1, not n. And for reasons I don't want to go into right now, this gives a better estimate of the parametric variance than just putting it over n. Okay, so that's the variance. Next I want to talk about standard deviation. Okay, so the standard deviation is symbolized by sigma, and it's just the square root of the variance for the population. And likewise, it's going to be the square root of the estimate of the variance for the sample population. Okay, so we have the standard deviation, we have the sample standard deviation. And then we have the standard error. And here's where people sometimes get confused. So I think people generally understand standard deviation and its relationship to variance. It's just the square root of the variance. But when we come to the standard error, things get a little bit confusing. So the standard error is the standard deviation of the distribution of the mean. And really, because we're talking about our parametric population, it's the distribution of estimates of this mean. And we don't usually talk about standard error much regarding the parametric population. We usually talk about the standard error, and it's sometimes given a separate name, but it's really the standard deviation of the mean. And we estimate that by dividing the standard error by the square root of n. All right, now there's a lot of theory that explains why that should be the formula for the standard deviation of the mean. But what I want to focus on here is what we want to use these quantities for. And for now, I'm going to focus on the sample standard deviation and standard errors. Okay, so when do we use standard deviation of observations, and when do we use standard deviation of the mean, i.e. the standard error? Okay, so if we are trying to understand where the observations lie, if we're making inferences about where, for example, 95% of our observations lie, so we are plotting y sub I on this axis, and we want to, for example, exclude 2.5% of the observations here and here on both sides of our estimate of the mean. We would, if we had, for example, n equals 60, we would recognize that we would have the mean plus 2 standard deviations, or the mean minus 2 standard deviations, and that would give us these points. So in other words, 95% of our observations fall between the points x bar plus 2s and x bar minus 2s. All right, so is that useful? Yeah, I mean, if we want sort of confidence limits on some observations, if we want to know whether it's reasonable that some observation falls within our sample or not, we can use that. But it's not very good for testing means. And very often, most often I would say, we are testing differences among means, for example. In which case, we are going to want to understand our confidence in our estimate of the mean, not our understanding about where observations should lie. Okay, so we are going to definitely have a narrower distribution, right? Because we have plus or minus 1 standard or 2 standard errors. So 95% of our estimates of the mean, when drawn from a parametric sample with mean mu and a standard deviation of sigma, and our sample size n, 95% of the time the mean will be plus or minus 2 standard errors. And so this has the specific meaning of our confidence interval for this mean estimate x bar. In other words, 95% of the time our true parametric mean would fall in this range given that sample size. And here we're talking about an n of 60. And I mentioned before, obviously this value would be different depending upon different n's, right? It would be quite a bit bigger than 2 if we had a very small n, and because we would have a very poor estimate of the mean, and we could get wildly different sorry about that. We could get wildly different estimates based upon how big our sample size was. Or if we had a very huge sample size, we could get closer and closer to our estimate. And why does it make sense that the standard error gets smaller and smaller? Because remember what it is. It's the standard deviation divided by the square root of n. And as this gets large, the denominator is small. Right? And the denominator gets large. The denominator is large, and therefore our total fraction gets small because the denominator here is large. So as n gets large, I just said that the other way around. I apologize for that. If as n gets large, the denominator gets large, and therefore 1 over the denominator is small. So our standard error gets smaller the larger n is. And so our confidence limits get narrower the bigger n is. It's kind of why the basic understanding of why we want to have a large n when we're trying to get a good estimate of the mean. We will be able to detect significant differences from hypothesized means, for example, or from other means if we have a large sample size, because our denominator here is getting smaller and we have more and more confidence that our mean reflects the true parametric mean. So if there is a difference between groups in some way, we will be able to detect a smaller difference the larger the sample size is. Okay, I just wanted to clarify for you the difference between plus or minus 2 standard deviations of observations and plus or minus 2 standard deviations of the mean. Typically, it's this one that we're going to use. This one has to do with telling us where observations lie around our estimated mean, where 95% of the observations lie. Okay? Alrighty. Have a good one.